Okay. Okay, thank you. This is joint work with my thesis advisor at Sapienza, Federico Ricci Tersenghi. And this is the work of my master thesis, so let's get into it. So this is an inference problem. The first thing we have to define are our variables, and these are capital N angles that are variables between 0 and 2 pi. And then we take measurements of these angles, pairwise measurements. With probability p, a measurement is just affected by a small error, which is a variance of order epsilon square. And with probability 1 minus p instead, it is completely uninformative, meaning that it's uniformly distributed on the circle. So we can distinguish between good measurements, this is what we call this kind, and bad measurements. And we can define a latent variable, which is the graph of good edges, which is defined in the following way. The vertex set is just 1 through capital N. And the edges, there is an edge between vertex I and vertex J whenever the corresponding measurement is good. For the moment, this graph here is distributed as an Erdős-Rényi random graph with n vertices and probability p. Okay, we'll forget about this guy for the moment and go on with the inference. So the question, of course, is we're given the measurements and we want to find the angle. And we have these 3 parameters that we can tune and see where is weak recovery possible. Okay. Delta were the measurements, delta ij. So it's the set of measurements. We have n choose 2 of them. Okay. So you write your Hamiltonian and the posterior and everything, and this corresponds to a fully connected pairwise graphical model with this quite ugly Hamiltonian, just to show it to you. And at this point, what do we expect? I mean, we expect that there will be some kind of trade-off between the number of good measurements and their precision. We also look at this kind of scaling of the variable. So we define p hat and epsilon hat in the following way. And we assume that they both go to 0, p and epsilon go to 0 as a power of n. And then we look at the plane epsilon p. Okay.
Remind me that p and epsilon were? P is the probability to have a bad measurement?
To have a good measurement, and epsilon is the variance of the good measurements. So we have a small error on the good measurements too.
But do you work with directed edges? Because the delta ij is not symmetric.
They are skew symmetric, of course. So delta ij is equal to minus delta ji. These are a set of 1/2 n times n minus 1 measurements. And so you only have them for example, I less or equal than j. Okay?
Yes, same for the noise.
Same for the noise, yes. Yeah, otherwise it's not interesting. Okay?
Are they modulo 2 pi, the angle?
Yes, it's all modulo 2 pi. We're all on the circle, and this gives quite a lot of problems. So if you're like me, the first thing you do is you hit this problem with BP and other message passing techniques. These are the equations. One would like to relax them in parametric form, but unfortunately, this is quite hard to do. For example, you would like to do AMP or stuff like that.
The graph is dense or no?
Yes, the graph is dense. The problem is there are twofold. The first is that the probability distributions on the circle are quite nasty. And then there is the fact that this form of the potential with this form of the potential is quite hard to find a class of probability distribution that is closed under the iteration of BP. This is the idea. also it's dense, but the interactions are not always small because it really depends on which point of the p hat epsilon hat plane we are in. So what we can do instead is, for example, linearize everything, and we can study the stability of this fixed point and study numerically what happens near the fixed point. Turns out that as soon as as we are above the instability threshold, we have a positive correlation between the top eigenvector of the non-backtracking matrix and the Planck signal. So this is a good a first algorithm to look at. And we can isolate this region in the p hat epsilon hat plane, which is where the message passing techniques work in general. So for p hat greater or equal than 1/2, we succeed in recovery, otherwise we don't.
What's the difference between P and P hat and epsilon and epsilon hat?
Yes. They were just rescaled this way. Okay. Okay, so what else can we say about this problem? The first thing we do is, well, to make calculations easier, we look at this form of P out. And one can derive an information theoretical bound which excludes a whole region of the parameter space. And this is the one you can see in red. And then you can see what other thing people have come up with in literature. And these are, for example, semi-definite programming methods. So you basically relax the problem to a convex one, and at the end you try to see if the solution makes sense. You can do an annealed version of expectation maximization. I don't want to get into what these algorithms are about. Or the state of the art, for example, this multi-frequency method. They're very complicated. But the point is that all these methods stop working right at p hat equals minus 1/2. And we don't know what's in between. There's this kind of gap. And we would like to see what's in there. So what's the problem with all these algorithms? They don't seem to exploit the fact that the good measurements are very precise. So remember, epsilon is n to the power of epsilon hat. And epsilon hat is less or equal than 0. So this, the precision of the measurement goes to 0 with, when n diverges. And all these kind of mean field algorithms do not exploit this fact, and in fact they just crash on the p hat equals 0.5 threshold, which is the best you can do also information theoretically. Okay. So instead, we can try to do a different thing. We look at the latent variable of the problem, which is the graph of good edges. And we first decide to, given delta, we decide to find the graph. And then, given delta and the graph, we find the angles. The second part is easy. I don't want to explain you why, but just believe me. So now the problem has become this one, basically. It doesn't sound like a good idea because we are asking for more than we want. We wanted just the angles, and now we are trying to break this problem into two and find a latent variable which we don't actually need. But the general theme is that of trading more information for computational efficiency. And in fact, it turns out that if you find the graph, then there are polynomial algorithms which are easy to implement. So how do you find the graph? Basically, you want to exploit information about the cycles. If all three edges on a cycle or a triangle or all edges on a cycle are good, then when you sum them, you are summing differences, and so you get something that is close to 0. Okay? and this is the inequality. So you can actually, and it's important, this is a local condition, so only we can use this to build the graph, looking only at few vertices. We don't need to infer it all together. Okay? So using this kind of conditions, one can understand which edges are good and which are bad. And the idea is that this formulation is more sensitive to epsilon, because the support of this measure, which ideally should be a point mass if we were able to fully recover the graph, greatly shrinks when epsilon decreases. And so we are exploiting this time information about the precision of the measurement that we have at our disposal. Yes? What's? Oh, you can actually devise an algorithm for each length. So you choose the length, and then you devise an algorithm for each length. And each algorithm, you get a hierarchy of algorithms, and each algorithm has a different threshold. For example, I choose like a triangle, but in the next slide we are going to look at squares. So you can, of course, the longer the cycles and the more you have to tolerate noise. So if I had chosen a cycle of length 4, this would have been 4 epsilon, and the condition is less strict. So you should prefer smaller cycles, because they are the ones that preserve the information more, because they are affected by less noise that accumulates when you sum the variables. Okay. I don't know if that answers your question.
You assume that you have them. I mean, you see a very so that you have triangles of this kind.
Yes, you do. No, you can count the expected number of cycles of a certain length, and you have them. Yes. Okay. So, how do you do this practically? You grow the graph. So the first thing you do is you look for a triangle. You start your algorithm like this, and with high probability you find one as long as p is greater than 1 over n. So that's sure. And then you fix an edge, and you look at all cycles of length 4 based on that edge, and you ask if they satisfy the condition. If they don't, you don't add them. If they do, you add them. And so you gradually build your graph in this way. Okay. And at this point, you want to understand if your algorithm will be successful. When is it successful? Well, the first condition is that there are enough cycles, and this poses a limitation on p hat. In this case, you are adding squares, and p hat must be greater or equal than 2/3. In the general case, where you're adding cycles of length L, p hat must be greater or equal than L minus 2 over L minus 1, something like this. Okay? And then, of course, you have to make sure that you are adding only the good edges to the graph and not the bad edges. I mean, it could totally be that this condition is also satisfied by chance by 3 edges that were bad, because they sum the errors sum to 3 epsilon. And to make sure there are not many of these false positives, so false good edges, you instead have to require that epsilon hat is less or equal than 3 p hat. And you can model this, so the analysis is done considering this algorithm as a Burton stochastic process. So each time you consider an edge and try to form cycles using it, you add more edges, but you expand one edge to look for more cycles. And so you have to make sure that you add more edges than you spend, and this gives you the condition. And finally, we see that this algorithm manages to break into this region, and you get the you get to p hat equals minus 2/3. And that's it. I'm done. Thank you.
Thank you. So while the next speaker is preparing and changing the computer, we have time for one question.
Why do we expand by like squares, not triangles?
Oh, because with triangles, you would obtain the same threshold as the other algorithms. That is p equals p hat equals minus 1/2.
And I had a question, like in the synchronization problems, how do you motivate this type of noise that some of the edges are very noisy and some of them are very precise? Like when does it arrive in practice?
Oh, I actually don't know, but I kind of got the problem and I studied it this way. But I know there are settings where you have like to synchronize clocks and they communicate with each other, and sometimes the communication is totally unreliable, and so a difference is random.
But I would expect the P to be small, not to be so big. But okay, you can take that offline.
Oh.
So the next talk is by Lorenzo on the community detection and sparse time evolving graphs with dynamic detectability.
Does it work? Sorry. Okay, so what are we talking about? The problem of community detection is a very well studied problem that, given a graph, especially a social graph, we typically have a mesoscale structure, in the sense that we have communities in which nodes belonging to the same community get connected more often. So you're given the graph, and with an unsupervised algorithm, you want to assign to each node its correct label. Doing the literature of this is kind of impossible. It's one of the most studied problems, I think. But the fact is that most of the algorithms concentrate on a static graph. But in reality, most of the graphs are dynamic. For example, human proximity, two people are connected if they're close to each other, if they are at the telephone, or two countries are connected if they trade, or there are examples in biology, or for example, a collaboration network. Two authors are connected if they publish a paper together. The idea is that evidently all these graphs evolve with time, but not only the graph may evolve, but also its mesoscale structure. So for example, you have a researcher that moves from one lab to the other, and it changes its co-authors. So the underlying idea is that we have a two time scale assumption. One time scale is the time at which the graph evolves, which is typically quite fast, at least in our reference frame. And the other one is the time at which the community evolves, which is supposed to be a much longer time. In many of the existing literature in dynamic community detection, however, the evolution of the community is essentially thought as frozen with respect to the evolution of the graph, which is essentially we remove the fun from the dynamic of the evolution. So our goal is twofold. On one hand, if we have many observations of the same graph, we expect the communities to be correlated, so we expect to do better than a single, by reconstruction with a single graph. But in the meantime, we may be able to have a very small correlation, and we want to be able to exploit the little we have. So the model is called dynamical degree corrected stochastic block model. It's a hidden Markov model. The hidden variable are the labels. I will talk about only two communities for simplicity, even if here there are four. So we assign to each node a label, and at each time the label is kept with the probability eta. Remember, eta is important, the probability with which you keep the label, and you reassign it at random with probability 1 minus eta. Once you have all the labels, you generate the graph independently according to a static DCSBN, which is the node I is connected to node J at time t with a probability proportional to Cin if they are in the same class at time t, and to C out otherwise. the term 1 over n is what makes the graph sparse, and theta I and theta j allows us to have an arbitrary degree distribution. So this is like what the evolution of the graph looks like. This is the adjacency matrix. At t equals 4, in the correct basis, it would look just like the same. So our goal is to assign the labels at each time step. So there is a main important thing for graphs generated from the degree corrected stochastic blob model that has been studied deeply in the static regime, which is also true in the dynamic regime, which is a detectability threshold. Hence, a condition on the parameter of the generative model below which you cannot say anything on the graph. So C is our average degree. Lambda is the other important parameter we have to remember, which is essentially the covariance. So C in and C out are the probabilities to get connected to a node in the same class and to the other class. So it quantifies the hardness of our problem. And alpha is the control parameter. So essentially we build this graph where we put in a sequence all the graphs we have. So G at time t, t plus 1, t plus 2. The labels are depicted with colors. We have the edges, and then we add for each node an edge to its like temporal sum. So we create this big graph. Since the graph is sparse, it locally converges to a multi-type branching process. What does it mean? We consider the node in the center, this one, which we call the root, and then its neighbors, or sun, better, will have the same color, the same class label, with probability lambda if the edge is a spatial edge, and with probability eta if the edge is a temporal edge. So then here we can study the problem more easily, and it locally converges, the graph above locally converges to a structure like this. So it was conjectured for t to infinity, so t is the number of graphs we observe by Gazemian, and we made it explicitly for finite t, the expression of the detectability threshold for arbitrary t and level persistent eta. Essentially, we see that for t equal to 1, this is the static result. As we increase the number of observed edges of observed graph, we can solve easier problem. Alpha has to be larger than a smaller number. And when we increase the persistence, also we improve. The big thing you have to remember is that we have an expression for alpha c, essentially. So the main result, how do we approach this problem? There is a solution in the literature which is base optimal, which is Bailey propagation. We look for something faster, even if less accurate. We use an Ising proxy. So we consider the graph which we built before, and we have an Ising Hamiltonian in it. So we sum over all edges, and then we have this coupling term for all the nodes at the same time, which depends on arctangent of psi. And then we have another coupling for the temporal edges, which depend on h. What is the idea behind that? Is that essentially here we are, the most energetically convenient configuration are those in which neighbors are aligned, essentially. The spins are aligned. Of course, this is a ferromagnetic Hamiltonian, so the ground state is where everybody is aligned. However, we expect to have other metastable configurations that recover the communities. And we have two different weights for those that are the spatial edges and the temporal edges. Now, this is quite standard, but we are on a graph, on a sparse graph, so we apply a tree-like approximation, which is called beta approximation, on the variation approximation of the probability distribution. We obtain the beta free energy. Once we have this, we study the beta Hessian matrix, which is the Hessian matrix of the beta free energy at the paramagnetic point. So the beta free energy is a function of the moments. When we are at high temperature, this function is convex, and the paramagnetic point m equal to 0 is a minimum, and its eigenvalues are all positive. When we have the first eigenvalue that turns negative, it's the paraferro phase transition, and the eigenvector points towards the ferromagnetic phase transition. As I said before, we expect to have other local minima that are metastable, which are correlated to the modular structure. So we expect that in the negative eigenvalues of this eigenvectors, we can find information about the community structure of the graph. Now, this matrix, it takes this form. It's, we have on the diagonal some blocks, and then this is the interaction term between the different times. The main question we have is that it depends on the couplings between the edges, which is psi and h. So, what is the good choice for psi and h? Of course, good for us, it means that we can go down to the detectability threshold. So, this is the main proposition, which is not a theorem because it's not rigorously proved. So, we choose lambda d equal to alpha c over square root of c phi. Alpha c, we know it. We don't need, it's a quantity that we can compute for any graph. It's almost independent of the graph. Then, in the thermodynamic limit, the smallest eigenvalue of the bulk, which is this purple thing, tends to 0 plus. And if we are above the detectability threshold, among the negative eigenvalues, there is at least one which is informative. I underlined it indeed. There is at least one. We don't know how many there are, but there is at least one. This is all we can say. Why is it important? Because we have no idea where it is, essentially. So this is the case for two communities and two times. This is what the metastable configurations look like with the hand. So we have the ferromagnetic configuration, which is always the ground state. Then we have a configuration in which the spins are aligned according to the community, and they are kept across time. Then we have a configuration in which nodes at the same time are aligned, and this is like this but flipped over time. Of course, we know that this is energetically more convenient than this, but we have no idea what is the relative position between these two. Now, this is already hard. Imagine when you have arbitrary k, arbitrary t, you have just everything that gets mixed. So the main result of the proposition is that we know that for certain, among the negative eigenvalues, they are the ones that are useful to reconstruct communities, but we don't know where they are. So in practice, what we do is just we take them all, we verified empirically that this allows to make a low-dimensional mapping, where then you can apply something like k-means to reconstruct the communities. This way to act is redundant, because essentially we don't need all those eigenvectors, but it does not compromise drastically the performance of the community detection. So a bit of performance comparison. So on the left we have the performance in terms of overlap. The overlap goes from 0, bad, to 1, very good. In terms of alpha, which I recall is the hardness of the problem, alpha should be greater than alpha c, which is this black line. And eta equal to 1 means very persistent, eta equal to 0 means independent. So on the left, this is our algorithm, where we can clearly see we can reconstruct communities as soon as theoretically possible. Whereas this is another approach in the literature that essentially consists of taking the average of the adjacency matrix. And this has the problem that essentially does not consider, is not able to solve the problem when eta is small, so when you have a small correlation. So a truly dynamical model cannot be solved like this. Now, we take a cut of this graph at eta equal to 0.7, and we have this graph, where we have different other models I compared to. So, two big things to notice is this region, which is hard problems, is where we really gain a lot with respect to the others. And this is the base optimal solution. So essentially, you cannot do better than BP. What is the good news is that we are approximately 500 times faster than BP. So if you want a fast answer, our algorithm is better. Or
which implementation of BP did you compare?
the one of the authors of Gazemian. They gave me the code and I ran it.
Well, we have our own version for the
But
multilayer network.
for the dynamical?
Yeah.
I didn't know. I think you can implement it faster, but in any case, a spectral algorithm will be faster than BP. A good thing would be to initialize BP to the solution we get with the spectral algorithm.
That's what we do, by the way, in our paper.
Okay, because what it does in the other one, I think it initializes to a random point, so it takes a lot to converge.
And what's the time here? What's the number of layers in the thing?
It's either 4 or 5. but we also run it for, because here we try to have a large number n of on nodes. This is 25,000, which is not written. But of course, if you have t equal to 50, you have smaller graphs. Otherwise, they don't fit in the memory. So that's pretty much it. So we proposed a fast algorithm to reconstruct communities as soon as theoretically possible, which exploit the positive correlation of labels. So we go where most of algorithms cannot go. And even if there is no label, almost no label persistence, but this is the big thing. The reason why we made the choice of lambda d and not something else is that given an arbitrary graph which is not generated from the degree corrected stochastic block model, you can implement our algorithm, and it kind of works. I cannot say it works perfectly on any graph, but it's well defined on any graph. Thank you for your attention.
And while the third speaker is preparing, do we have questions for Lorenzo? Who's the third speaker? Oh. Well, if not, let's thank Lorenzo again and finish the speakers.
Oh.
Do you mind this?
The latter. Great.
So, last speaker today is Tiffany on constraint-based regularization of neural networks.
Hi, yeah, so I'd like to talk to you about my recent preprint on constraint-based regularization neural networks, as you just said. So this is joint work with my supervisor, Ben Lijmkuller, a postdoc Timothy Pachol, and Amos Storkey at the informatics department, all at the University of Edinburgh. So I'm assuming everybody knows what regularization is. So examples of regularization are like L2 regularization, which is where you add a penalty term to the loss to penalize your weights not to become too big. So this is a form of explicit regularization. Then there's also techniques already out there, such as batch normalization and dropout, which already cause some sort of implicit regularization effect. In this work, we will impose constraints directly on the parameters of the neural networks themselves, so on the weights of the network, using this stochastic differential equation framework. So we'll be using constraint SDEs. And so let's first see how these SDEs arise in training of neural networks. So we all know gradient descent. So you update the parameters of your network theta in the direction of the negative gradient of your loss, which we know by G, and you have step size H. So if you subsample, you introduce some noise into the system, and you get a stochastic gradient descent where you have a perturbed form of your gradient. And so you can approximately model this as follows, where sigma times its transpose is the noise covariance matrix. R is a standard normal vector with IID components. And so probably most of you already recognize this as Euler-Maruyama discretization of this SDE. So Euler-Maruyama is just the stochastic counterpart of Euler discretization for ODEs. And so W here is a Wiener process, which has Gaussian independent increments. And so the interesting thing about this SDE is that the step size H appears in this term. So we're dealing with a multiplicative noise term. And so the size of this noise will depend on the step size you use, your batch size. And this SDE has an unknown invariant distribution because the complicated form of the gradient noise. So what we want to discuss here is if you add additive noise. Yes, it's happening. So this is STD. So if you add some additive noise term, you arrive at the stochastic gradient Langevin dynamics method, which was actually developed by Max Belling, who was here last week, and Tay in 2011. And so the idea of this method is that if you have a small enough step size, then the additive noise term will dominate. So in their paper, they say if you take a decaying sequence of step sizes, then in the end, you actually expect to sample from the invariant distribution. And so it's a sampling method. But then in practice, you don't really want to use such small step sizes. So you accept some bias in return for faster mixing. But the thing about this method is that it doesn't mix as well. So let's look at the case where you try to add momentum to accelerate convergence. So then you arrive at this scheme, which is called underdamped Langevin. And so basically what this consists of is a Hamiltonian part, which is this part, and then a stochastic part. And so this is your additive noise term in that case. And so this kind of dynamics, you can also show to be ergodic, so it also samples from this invariant distribution where this is your Hamiltonian, so your potential energy, kinetic energy. And so the interesting thing about this chow parameter, so that controls the size of your additive noise, is that it actually can provide a link between pure optimization and Bayes. So if you set it to be 1, you recover the Bayes posterior. But if you take it close and close to 0, you will zoom in more of the modes to the modes of distribution, and in the limits, it can be seen as optimization. And so recently, there was a paper called Cold Posteriors, where they actually show that if you take very small values of tau, that you can actually get quite good results. And so they actually cite the paper that I'll mention on the next slide, so my paper. Let's see. Right, so we have this, and now there's one more equation, and then we're done. So what I didn't mention here is that, of course, here your this gradient is perturbed, right? Because we subsample the data. So can we maybe get rid of some of this excess noise? So our idea was maybe, so we looked at this adaptive Langevin method, which is kind of a cool idea. So what they do there is that they reinterpret this friction variable here as a dynamical variable. And by having this auxiliary variable here, they have some sort of feedback law. And so the idea of this is that you can kind of dissipate excess noise as a sort of thermostat idea, where you can maintain the correct energy in the room, the correct temperature in the room. And so the idea is that you still have the same invariant distribution. And so we looked at this in this work. And in addition to looking at this, we also partitioned the network based on natural layer structures. So we used different optimizers for different layers. And this also turned out to be advantageous. But there's a lot more to investigate in this area. So we're still working on like a follow-up paper for this. But if you're interested, let's talk about it. But here I want to talk about constraint SEs. So let's consider a constraint in the following form. So we have a equation of, we have a function that's dependent on our parameters theta of our network. And we say that our general constraint equation is that g theta is equal to 0. So I'll discuss some specific constraints in the next slide. But we have a general framework for this. And so then a natural thing to do if you do a constraint optimization problem is to look at Lagrange multipliers. So we did. And this is for the overdamped Langevin case. So this is with some additive noise but no momentum. Yeah. So it's just one constraint. So I'll give some examples. It becomes clearer on the next slide, I think, of some specific constraint. So here on this slide, I just want to say that you can also show that there's an underlying ergodic SE for this. And if you discretize this, what you essentially do is an Euler-Mariana step for the SE and then project it back to your manifolds. And so just ensure that your initial conditional base constraint, that's important. And then if you want to look at the momentum case, so this is the underdamped Langevin case where we had that second order dynamics. Then you also have an additional cotangent condition that you want to obey. So discretizing this gets a little like convoluted, but all the details are in the paper. So yes, so check that out. I think it's a bit too much for this presentation. So now let's look at some specific constraints. So an example of a constraint equation is where you put theta to be this. So in this case, this is what we call circle constraints. So it essentially just constrains the magnitudes of your weights. And so what we do is for each constraint parameter, we introduce an additional slack variable xi. And then obviously this just defines the circle, right? Because we set the constraint g to be equal to 0. And so we also looked at orthogonal constraints, where you impose orthogonality of your weight matrix. And so orthogonality has been used a lot for mitigating the vanishing exploding gradient problem for recurrent neural networks. But recently there was also a paper where they looked at very deep convolutional networks, and they used orthogonal initialization, which turned out to be advantageous. So there's more techniques out there where they can impose orthogonality during training, but it was quite natural for our method as well. So yes. And then, well, there's many other options because of the generality of the framework. So if anybody has an idea for that, come talk to me, and obviously we'll keep on working on that as well. So then some experiments. So this is for the search constraint case. So we looked at fashion MNIST, where we reduced the number of training data samples to, tease it to get overfit a bit more. And so what we did is we looked at SG momentum and then basically its search constraint counterpart, where we set additive noise to be 0 to make a fair comparison. So our method, which has a crazy convoluted name, but that's a blue one, outperforms SGD. So of course we did like a swap over the hyperparameters, and every time our method was slightly better. But mostly if you look at the test loss, you can see that SG momentum like goes up like crazy and then hurts down here. So
What is the motivation to constrain the data set?
oh, so it's basically like ultra regression if you want to constrain the magnitude of your weights. Yeah, so it's just a easy way to do that. And you have a little bit more flexibility than. So for the orthogonal constraints, we looked at tightly wound spiral data with multi-layer perceptrons, and then we varied the number of hidden layers for the perceptrons. And so we looked at SGD both without orthogonal initialization and with orthogonal initialization, and then this is our method. And so standard SGD can't really handle very deep multi-layer perceptrons, so it does quite poorly. With orthogonal initialization, it does a little bit better, and then ours is like quite nice, although it performs less well with less hidden layers, so that's quite interesting. So, and then, well, we submitted to NERB, so we had to do something with resonance, so we did that as well. So this is also for orthogonal constraints. And so first we did just standard SGD versus the constrained version. And so it seemed to overfit slightly less and have a slightly higher accuracy. But then, obviously, we needed to compare it to like more state-of-the-art. So we did SGD with momentum, with weight decay, and with learning rate decay. So that's where we decay the learning rate, is at these like vertical bars. And there, our method was equally good as the case with weight decay, which is like orange. So our method is green, and orange is with weight decay, so it does a little bit better with weight decay. But we do a lot better than without weight decay. So optionally, also there's like a lot still to optimize about this method. So yes, I think that was about it. Any questions? Yes. So actually most of our experiments we didn't actually add the additive noise because we wanted to make a fair comparison with SGD and SGD with momentum, but it does allow for this additive noise. And the idea of that is that you would have a little bit more exploration. Of course we had like a whole discussion this morning in the lecture about maybe not needing this for neural network loss landscapes. But I still think for certain kind of training problems, it does seem like you have slightly more complicated loss landscapes, and it seems beneficial to have this additive noise. So that's what we have in the paper I mentioned earlier. So it's like examples like the tightly wound spirals, and we have, for example, poker data set where it seems to like make a difference. So I don't know, there's still some research to be done there. So, but obviously a lot of things point towards over-parameterized neural networks maybe not needing this additional exploration, but I think there's still something to be seen there. So, but anyway, it allows for adding that if you wish. Yes. Yeah, and for the convnets, we kind of, how do you say it in English? We regroup the weight matrices, kind of, so we, yeah, but essentially per layer. I can't think of the right word now, but yes. Okay. Yeah.
Okay, cool. You can definitely. So, other questions for the dinner?